Hello everyone, my name is Pujita and today I am going to tell about the topic called Universal Logic Gates. Here in Universal Logic Gates, we are going to discuss about NAND gate, NOR gate, implementation of NAND gate and implementation of NOR gate. What do you mean by Universal Logic Gates? They are fundamental building blocks in a digital electronics. These gates are used to represent any types of gates or circuits. Here, Universal Logic Gates are NAND and NOR. Next, NAND gate. NAND gate is logically equivalent to AND gate followed by a NOT gate. The truth table for this gate shows that the output of NAND gate is low only if all its input are high. Here, this implies that the output of the NAND gate is the negated output of the AND gate. It is represented by the intermediate result M in the truth table. The logical expression for the NAND gate is y equals to A into B whole bar. Now let us see the truth table of NAND gate. Here we are taken two inputs A and B, and the intermediate output of this gate represents the output of the AND gate, and the actual form of output is the negated output of AND gate. Now let us see the symbol for NAND gate. Here AND and NOT gate, on both combination we are going to get NAND gate. For the NAND gate, if we are given AB as input, we are going to get output as A into B. For the NOT gate, we are going to use only a single input. So A into B. That output is given as A into B whole bar. Here the NAND gate logical expression is also represented as A into B whole. Now let us discuss about NOR gate. NOR gate is a result of combining NOT gate with an OR gate. This output is the negation of OR gate output, which implies that it has high output only if its inputs are low. However, for any other combination of inputs, the output will be low as shown by the truth table. Here the logical expression is given as y equals to A plus B whole. Now let us see the truth table for NOR gate. Here we are taken with AB as input and intermediate output represents the OR gate output, and the final output is the negation of the OR gate. Now let us see the symbol for NOR gate. Here OR and NOT gate represents the NOR gate. If we see AB are taken as inputs and for the OR gate we are going to get A plus B as output. Furtherly, for NOT gate we have to use only single input. So here A plus B is used as single input and the output we are going to get as A plus B whole bar. Let us see the implementation of NAND gate. Here we are going to represent our NOT gate using NAND gate. As we know the symbol for NAND gate, and we also know that for NOT gate we are only using a single input. Here we are taken as A as single input and we are going to get our output as the negated value for A. It says that the output of this NAND logic circuit is equivalent to the NOT gate output. So it is given as y equals to A bar that equals to A comma. Now let us represent our AND gate using NAND gate. For representing AND gate using NAND gate, we are going to use two NAND gates. Here we are given with A and B as input, and for this first NAND gate, we are going to get the output as A into B whole bar. And this is again generated into second NAND gate, which is furtherly going to get as A into B. And here the logic expression we can say as y equals to A into B. Let us represent our OR gate using NAND gate. For representing this OR gate, we are going to use three NAND gates. And here we are taken with two inputs A and B. For the first NAND gate, the input is A and the output we are going to get as A bar. For the second NAND gate, here we are taking B as input and the output is going to get as B bar. For the third NAND gate, here A bar and B bar are taken as inputs and the output is given as A bar, B bar, whole bar. By using De Morgan's law, we are going to represent this A bar, B bar, whole bar is equals to A plus B, which is the simple form. For the OR gate, the logical expression is A plus B as. Now, let us see our XOR gate using NAND gate. For representing our XOR gate using NAND gates, we are going to use 4 NAND gates. Here we are taken with AB as 2 inputs, and the whole thing is representing to derive the equation for XOR gate. Here if we observe, in each step by step, we are using last to simplify the equation to get our exact logical expression. At final output, here it is represented as y equals to A exclusive B. It can also be written as A plus B into A into B whole bar, which represents the XOR gate logical expression. The actual symbol of XOR gate is shown above with the symbol and the logical expression. Now let us see our XOR gate using NAND gate. To represent our XOR gate using NAND gate, we require 5 NAND gates. As usual, taking the AB as inputs, we are going to get the XOR output. By using these 5 NAND gates, we are going to derive to get our XOR expression. In each gate, we are going to use different laws to derive the expression. The original gate of XOR is given as above, and the logical expression is given as y equals to A exclusive B whole bar. Now let us represent our remaining gates using NOR gate. First, let us see our NOT gate using NOR gate. To represent this, we are taken with NOR gate and NOT gate. On combining that, we are going to get our NOT gate using NOR gate. We know that for NOT gate, we have to take only single input. So A is taken as single input, and we are going to get output as y equals to A bar. This is the representation of NOT gate using NOR gate. Now let us see our OR gate using NOR gate. Here the NOR gate symbol is given as above. For the input of AB, we are going to get output as y equals to A plus B whole bar. For the symbol of NOR gate, there is a small bubble which represents the inversion of the input, and the OR gate symbol is given as above. For the input of AB, we are going to get the output as y equals to A plus B. On combining the both, we are going to represent our OR gate as the follows. For input AB, for the NOR gate, we are going to get A plus B whole bar. And the A plus B whole bar is taken as input to the next NOR gate. We are going to get our output as y equals to A plus B. Now let us see our AND gate using NOR gate. To represent our AND gate using NOR gate, we are going to use 3 NOR gates. If we see here, A and B are taken as inputs, and for the A, we are going to get output for first NOR gate as A bar, and the B as input for the first NOR gate is going to get as B bar. On taking A bar and B bar as inputs, for the third NOR gate, we are going to get the equation as follows. That is y equals to A bar plus B bar whole bar. By De Morgan's law, we can write that as A into B bar whole bar. We know that A into B bar whole bar is equals to A into B. The symbol of AND gate is given as follows, and the output is said as y equals to A into B. Now let us see XOR gate. To represent our XOR gate using NOR gate, we are going to use 5 NOR gates. AB are taken as input here, and through each gate they are getting inversed, and we are going to get the value of XOR gate. At last, XOR gate logical expression is y equals to A exclusive B. For XOR gate, if there are even number of ones, the output is going to get as 0. If there are odd number of ones, the output is going to get as 1. That is the truth table for XOR gate. At last, representing our XNOR gate in NOR gate. To represent this, we are going to use 4 NOR gates as AB taken as input, and in each gate they are getting inverse to get our XNOR expression. The actual representation of XNOR gate is given below. For the output input of AB, we are going to get output as Y equals to A exclusive B whole bar. Here the small circle represents the inversion values. Thank you.